Jupiter is slowly becoming something that could eventually reignite our entire solar system. Almost nobody knows that Jupiter, the largest planet in our solar system, is not just sitting there in the dark. It is producing its own heat. Right now, tonight, the interior of Jupiter is radiating almost twice as much energy as it receives from the sun. It is still slowly shrinking. Its core is hotter than the surface of the sun, and the only reason it is not a star is that it fell short of a specific threshold by a very precise amount. In this video, we will walk through 5 things together. We will look at what is actually happening inside Jupiter right now, and why a planet is producing more energy than it collects from its own star. We will look at the process that is driving that heat, a slow gravitational contraction that has been running for 4.6 billion years and has never stopped. We will walk through the interior of Jupiter layer by layer, from the cloud tops down to a diffuse core at temperatures hotter than the surface of the sun, including the strange layer of metallic hydrogen that makes most of Jupiter unlike anything on Earth. We will look at the number that separates a planet from a star, how close Jupiter came to crossing it, and what the objects in the range between a planet and a star actually are. And we will sit with what that almost crossing means for every living thing that has ever existed on Earth. By the end of tonight, you will understand why Jupiter is still, right now, slowly contracting. You will understand what helium rain is and why it happens thousands of kilometers below a cloud layer on a planet 5 times farther from the sun than we are. You will understand why the same failure that kept Jupiter from igniting is part of why Earth had billions of years of stable conditions to develop life. And you will understand why some planetary scientists do not call Jupiter a planet at all. They call it a failed star. And the word failed may be the wrong word entirely. So get comfortable. Pull a blanket over yourself. Make yourself something warm to drink. Let the lights go low. And let the world outside fade out. We're going to take our time with this one. If this kind of slow, careful walk through real science is what you have been looking for at the end of your day, please consider subscribing. It really does help, and I am genuinely grateful you are here. Now, let's begin. Let me start with something that most people, when they first hear it, assume is a mistake, a calculation error, something the textbook got wrong. Jupiter radiates almost twice as much energy as it receives from the sun. Read that again, because it matters. Jupiter is not close to the sun. It orbits at a distance of about 778 million kilometers, roughly 5 times farther out than Earth. At that distance, the sun's light has already spread thin. Jupiter receives only about 4% of the solar energy that Earth receives per unit of surface area. It is cold out there by any everyday measure. The cloud tops of Jupiter sit at around negative 145 degrees Celsius. Cold enough to freeze most gases on Earth. And yet Jupiter is putting out almost twice the energy it is taking in. The planet is not just reflecting sunlight. It is producing heat from within and pouring that heat outward into space at a rate that has no equivalent among the inner planets. Earth does not do this. Mars does not do this. Venus does not do this. They absorb energy from the sun and re-emit it, but they do not generate significant energy of their own. A rocky planet radiates about as much heat as it absorbs. The books balance. Jupiter's books do not balance. Astronomers first confirmed this energy imbalance in the 1960s. Using infrared observations, they measured how much solar energy was hitting Jupiter and how much energy Jupiter was radiating back into space. The numbers did not balance. Jupiter was radiating roughly 1.7 times more energy than it was receiving. For a while, scientists thought this might be measurement error. The atmosphere of Jupiter is complex. The clouds scatter light in unusual ways. Perhaps the calibration was off. It was not off. Later measurements confirmed and refined the ratio. The Cassini spacecraft, during its 2000 flyby of Jupiter on its way to Saturn, measured Jupiter's internal heat output at about 7.5 watts per square meter. That is roughly 3 times the internal heat flux of Earth's own interior, which releases about 0.09 watts per square meter from the decay of radioactive elements in the crust and mantle. Let me say what that means in a way you can feel. Every square meter of Jupiter's cloud tops is pouring out 7.5 watts of heat that comes from inside the planet. To put that another way, Imagine covering every square meter of Jupiter's outer surface with a dim nightlight, not a bright one, a 7.5-watt bulb. That is the amount of energy radiating outward from Jupiter's interior, across every square meter of its surface, every second. Jupiter has a surface area of about 6.1 times 10 to the power of 13 square meters. That is about 121 times the surface area of Earth. Multiply 7.5 watts by that surface area, and you get a total internal power output of roughly 3 times 10 to the power of 17 watts. That is 300 quadrillion watts of internal heat, generated by the planet every second. Not reflected sunlight, not absorbed solar energy. Heat that is being generated by something happening deep beneath the clouds, somewhere in the interior of a planet that is 5.2 astronomical units from the sun. The obvious question is where this heat is coming from. That question has 3 answers, and each of them is stranger than the last. The first answer is that Jupiter is not finished forming. That sounds like something is wrong with the statement. Jupiter is 4.6 billion years old. Our entire solar system is 4.6 billion years old. Jupiter formed in the first few million years of the solar system's history, before most of the other planets had even assembled their cores. It is, by any reasonable measure, ancient, and yet it is still contracting, still shrinking, still generating heat from the process of its own formation. Here is how that works. When Jupiter first assembled, it was a cloud of gas and dust, drawn together by gravity from the outer solar system's vast reservoir of material. As that cloud collapsed inward, it heated up. You have felt this principle yourself. When you compress air inside a bicycle pump and hold your thumb over the valve, the pump gets warm. Compressing a gas converts the energy stored in the gas's volume into kinetic energy, which you experience as heat. The same principle applies to a collapsing gas cloud, just at an almost incomprehensible scale. The proto-Jupiter, collapsing under its own gravity, generated enormous heat. At its peak, Jupiter was probably twice its current size and dramatically hotter. Theoretical models suggest that when Jupiter first assembled its current mass, its surface temperature may have been closer to 10,000 degrees Celsius. Over the following billions of years, it began to radiate that heat outward and cool down. It shrank. It cooled. The outer layers contracted inward, but it has not finished that process. 4.5 billion years later, Jupiter is still slowly contracting. The rate of contraction is about 1 millimeter per year. 1 millimeter per year. It sounds negligible, and on the scale of a human life it is. You could watch Jupiter for 1,000 years and not see any change in its apparent size through a telescope. The contraction is not visible. It is not dramatic. It is 1 millimeter per year, year after year, for billions of years, the most patient process in the solar system. But patience is its own kind of power. 1 millimeter per year, applied over 4.6 billion years, is 4.6 million meters, which is 4,600 kilometers. Jupiter has shrunk by roughly 4,600 kilometers since it formed. It was once about twice its current diameter. It is now about 143,000 kilometers across at the equator. The contraction is real, measurable, ongoing. The process is named after 2 physicists, William Thomson, who is better known as Lord Kelvin, and Hermann von Helmholtz, who worked out the thermodynamics of gravitational contraction in the 19th century. Both were trying to answer a completely different question at the time. Why does the sun shine? Before nuclear physics was understood, the leading theory for the sun's energy source was that the sun was slowly contracting, converting gravitational potential energy into heat. Kelvin calculated that this mechanism could power the sun for about 20 million years. Geologists and biologists were already arguing that the Earth must be billions of years old, based on fossil evidence and rock strata. The Kelvin-Helmholtz estimate was too short. The sun's actual energy source turned out to be nuclear fusion, not contraction. But for Jupiter, the Kelvin-Helmholtz mechanism is real. Jupiter is not powered by nuclear fusion. It does not have the mass to fuse hydrogen. What it does have is 4.6 billion years of slow contraction, still ongoing, and that contraction provides roughly half of Jupiter's excess heat output. The other half comes from a process that Kelvin and Helmholtz could never have predicted, because it was not discovered until the 20th century and requires physics they did not have. deep inside Jupiter, something happens that has no equivalent anywhere on Earth. It does not happen in any laboratory we have built. It does not happen in any weather system we have studied. It is a process that, when you first hear the description, sounds like it should be impossible. It is called helium rain. To understand it, you need to understand what the inside of Jupiter actually looks like, layer by layer, because the inside of Jupiter is one of the most alien environments in the solar system. The atmosphere we see, the swirling bands of ammonia clouds, and the famous Great Red Spot, is only the outermost skin. Below the visible cloud layer, the pressure increases with depth, just as ocean pressure increases as you dive deeper. At around 50 kilometers below the cloud tops, the pressure is already 10 times the atmospheric pressure at Earth's surface. At 100 kilometers, it is 20 times. The gas, which starts as something resembling an atmosphere, gradually becomes denser and denser as you go deeper, without any sharp transition from gas to liquid. There is no surface on Jupiter. You would not hit anything solid. You would just feel the pressure increasing, and the temperature increasing, and the gas around you becoming thicker and heavier, until you could no longer distinguish it from a liquid. By about 20,000 kilometers below the cloud tops, something happens that has no parallel in ordinary chemistry. The pressure at that depth is several million times the atmospheric pressure at Earth's surface. Under that pressure, the molecular bonds between hydrogen atoms break. Ordinary hydrogen, H2, exists as pairs of atoms sharing electrons. Under extreme pressure, those electron pairs can no longer hold their configuration. The electrons are squeezed so tightly that they begin to move freely from atom to atom, unbound to any particular proton. When electrons can move freely through a material, that material conducts electricity. Hydrogen, under this pressure, becomes a metal. Not a solid metal like iron or copper, a conducting fluid, a liquid metallic state of hydrogen that has no equivalent in ordinary chemistry. This state of hydrogen, metallic hydrogen, is one of the most exotic forms of matter in the solar system. It has been created in laboratories for fractions of a second, using extreme shock compression from high-powered lasers aimed at tiny samples. Those experiments last microseconds. Inside Jupiter, the metallic hydrogen zone extends for thousands of kilometers and has been stable for 4.6 billion years. Now helium. Jupiter's atmosphere is about 76% hydrogen and 24% helium by mass, roughly similar to the composition of the Sun. In the outer molecular hydrogen layer, helium mixes freely with the hydrogen. The two elements coexist without any tendency to separate. But in the metallic hydrogen zone deeper down, something changes. The same pressures and temperatures that turn hydrogen into a metal also change the chemical affinity between hydrogen and helium. Helium becomes less and less soluble in metallic hydrogen, the same way oil becomes less soluble in water as temperature changes. Helium begins to separate from the surrounding hydrogen and form droplets. Those droplets sink. They fall inward through the metallic hydrogen, toward the core, under the pull of Jupiter's gravity. The droplets are denser than the metallic hydrogen, so they fall rather than rising. As they fall, they generate frictional heat through the resistance of the surrounding fluid. That heat is deposited deep in the interior and eventually works its way outward to the cloud tops, contributing to Jupiter's overall heat output. The Juno mission has been measuring Jupiter's helium abundance with unprecedented precision. The results suggest that Jupiter's outer atmosphere contains slightly less helium than the planet started with, consistent with the picture of helium slowly raining inward over billions of years. Saturn shows an even stronger version of the same pattern, with a noticeably helium-depleted outer atmosphere compared to what models predict it started with. We have not seen helium rain. We cannot see it. The layer where it happens is tens of thousands of kilometers below the cloud tops, under pressures that would instantly crush any probe we could currently build. The deepest any probe has ever gone into Jupiter was the Galileo Atmospheric Entry Probe in 1995, which descended about 150 kilometers before it was crushed and vaporized by pressure and heat. The helium rain zone is over 100 times deeper than that, but the evidence for it is in the numbers. The heat output, the helium deficit, and the theoretical models all converge on the same picture. Helium rain is happening right now. At this moment, as you listen to this, Droplets of helium are falling through conducting fluid metal thousands of kilometers below the cloud tops of the largest planet in our solar system, generating heat, redistributing material, and slowly changing the composition of a planet that has been doing this for longer than there has been life on Earth. Before the Juno mission arrived at Jupiter in 2016, planetary scientists had a fairly clear picture of what Jupiter's core should look like. The leading models said Jupiter should have a small, compact, dense core at the center, rocky material, some iron and silicates, heavy elements that did not get swept up into the expanding atmosphere during formation. The core was expected to be around 10 to 20 times the mass of Earth, tightly packed at the center of the planet, with a sharp boundary separating it from the surrounding metallic hydrogen shell above. This picture was clean. It was elegant, and Juno showed it was wrong. Juno does not look like most spacecraft. It has 3 large solar panel wings, each about 9 meters long, arranged in a pinwheel pattern. It orbits Jupiter on a highly elongated path that takes it from high above the poles down to within about 4,200 kilometers of the cloud tops on each close approach pass. That is closer to Jupiter than any previous spacecraft had ever gotten, close enough to feel the radiation from Jupiter's enormous magnetic field rattling the instruments on board. On each close approach, Juno uses the extreme sensitivity of its radio tracking to measure tiny variations in Jupiter's gravitational field. The idea is that if you know exactly how fast Juno is traveling and exactly how that speed changes as it flies through different regions of Jupiter's gravitational influence, you can work backward to infer how the mass is distributed inside the planet. A compact core would produce a specific pattern of gravitational variation. A diffuse core would produce a different pattern. The data would tell the story. What Juno found is that Jupiter's core is not compact. It is not small and tightly bounded. It is diffuse, spread outward from the center into a zone that extends for perhaps 30 to 50% of the planet's radius. That is a remarkable number. Jupiter's radius is about 71,500 kilometers at the equator. 30 to 50% of that radius means the fuzzy core zone extends outward by 21,000 to 35,000 kilometers from the center. Instead of a sharp boundary between a rocky core and the surrounding metallic hydrogen, there is a gradual mixing zone, a blended region of heavy elements that shades slowly into the hydrogen mantle. How did this happen? The leading explanation involves a giant impact in Jupiter's early history. Shortly after Jupiter formed its initial compact core and began accreting its hydrogen-helium envelope, a large planetary object, potentially several times the mass of Earth, may have struck Jupiter at high velocity. The impact energy was so large that it partially disrupted and dissolved the pre-existing compact core, stirring the heavy material outward into the surrounding fluid hydrogen. The boundary between core and mantle was blurred by violence. The core became diffuse. There is an irony here. The diffuse core means that the heavy elements, the seeds of Jupiter's initial formation, are not neatly contained at the center. They are mixed throughout the deep interior. The planet's own violent early history, a history of enormous collisions during the chaotic period when the solar system was young and full of large migrating objects, reshaped its interior into something more mixed, more blended, and more surprising than the clean models predicted. The core temperature is estimated, based on current models of Jupiter's interior, at around 24,000 degrees Celsius. Some estimates put it as high as 35,000 degrees Celsius, depending on assumptions about the exact composition and structure. Even at the lower estimate, 24,000 degrees Celsius is roughly 4 times the temperature of the Sun's visible surface. The photosphere of the Sun, the surface you see when you look at it through a safe filter, has a temperature of about 5,500 degrees Celsius. Jupiter's core runs 4 to 6 times hotter than that. Jupiter is not a cold, dark planet sitting in the outer solar system. It is a hot object, intensely hot at its center, surrounded by conducting metallic fluid, still contracting, still raining helium, still generating heat from multiple sources and pouring it outward into space. The cold we associate with Jupiter is real, but it is only at the cloud tops. Below that, in the layers we cannot see and have never visited, it is a furnace running at temperatures that would vaporize any material known on Earth's surface. The cold face of Jupiter is not its true face. Its true face is heat. Now we come to the number. The threshold for stellar ignition, the minimum mass at which an object can sustain nuclear fusion of ordinary hydrogen and become a true star, is approximately 75 to 80 times the mass of Jupiter. Different models give slightly different values, depending on the assumed composition of the material and the exact equations used to model stellar interiors. The most commonly cited figure is about 0.075 to 0.08 solar masses, which works out to roughly 75 to 80 Jupiter masses. Jupiter's current mass is approximately 0.00095 solar masses, or about 1,000th of the mass of the Sun. That is a factor of roughly 80 below ignition. So Jupiter would need about 75 to 80 times more mass than it currently has to become a star. That gap sounds enormous. In human terms, it is. You could fit 75 Jupiters between Jupiter's current mass and the ignition threshold, and each of those Jupiters would contain more than 300 times the mass of Earth. The gap in actual physical material is staggering, but in the context of how planets and stars form from collapsing gas clouds, the gap is not as extreme as it sounds. The ratio between Jupiter's mass and the stellar ignition threshold is about 80 to 1. The ratio between a small mountain and Mount Everest is similar. Both are mountains. Both are made of the same rocks. The difference is accumulation, not kind. Here is the thing about Jupiter's formation. The outer solar system, in the first few million years after the Sun ignited, contained an enormous amount of material. The solar nebula, the vast cloud of gas and dust from which everything formed, was mostly hydrogen and helium, the same raw material as the Sun Jupiter formed early. In the first few million years of the solar system's history, it assembled roughly 90% of its current mass in what is, by geological standards, an extremely short span of time. And then the supply ran out. The young Sun, as it settled into stable nuclear burning, began emitting a powerful stellar wind. This solar wind, a stream of charged particles blowing outward in all directions, slowly dispersed the remaining gas from the outer solar system. Jupiter's accretion rate, which had been rapid in the early period, slowed, and then stopped as the available material became too thin and too scattered to fall inward efficiently. The planet had stopped growing. If Jupiter had formed a few million years earlier, it would have had access to more material before the solar wind dispersed it. If the solar nebula had been slightly denser in the outer regions, or if the young Sun had been slightly less luminous, the dispersal would have taken longer and Jupiter could have continued accreting. None of those things happened. The timing was what it was. Jupiter got what it got. Let me say what the number 75 means in one more way, because I think it is the most useful framing. If you could somehow transport 75 more Jupiters worth of hydrogen and helium to our solar system and pile it on top of Jupiter over the course of a few thousand years, the temperature at Jupiter's core would begin to rise. The core is already at 24,000 degrees Celsius. As you added mass, the pressure at the center would increase. The temperature would follow. At around 10 million degrees Celsius, ordinary hydrogen protons would be moving fast enough and close enough together for quantum tunneling to allow them to overcome their mutual electrical repulsion and fuse. The first nuclear reaction would occur. Helium would begin to form from hydrogen. Energy would be released. A cascade would begin. Jupiter would ignite. The process would not be instant. Stellar ignition is not an explosion. It is the beginning of a self-sustaining cycle. Fusion releases energy. The energy creates pressure that pushes outward against gravity's inward pull. If the two forces balance, the object settles into a stable, long-lived fusion state, a star. Jupiter needed 75 more Jupiters of hydrogen for that balance to be achievable. It had access to an enormous reservoir of that hydrogen for a few million years. And then the window closed. There is a class of objects that sits in the gap between what Jupiter is and what the Sun is. They are called brown dwarfs, and they occupy one of the strangest neighborhoods in the universe. A brown dwarf forms the same way a star forms. A cloud of gas collapses under gravity. The core heats up. The pressure increases. But the mass never quite reaches the threshold for sustained hydrogen fusion. What the mass does reach, for objects above about 13 Jupiter masses, is the threshold for a different, simpler reaction: deuterium fusion. Deuterium is a heavy isotope of hydrogen. Its nucleus contains one proton and one neutron, unlike ordinary hydrogen, which is just a proton. Deuterium fusion requires less pressure and lower temperatures than ordinary hydrogen fusion. For an object above about 13 Jupiter masses, the conditions inside the collapsing core become sufficient for deuterium atoms to fuse, releasing energy. The object briefly glows. It is warm enough to be seen in infrared. For a few million years, it is, technically, a stellar object. But deuterium is rare. The early universe produced about one deuterium atom for every 40,000 hydrogen atoms. A newly formed brown dwarf has only a finite supply of deuterium. Once it is fused, it is gone. The fusion stops. The object begins to cool. And unlike a true star, which is billions of years' worth of ordinary hydrogen to fuse, a brown dwarf's active period ends in millions of years, not billions. After the deuterium is exhausted, a brown dwarf glows only from its residual heat, the same heat that drives Jupiter's luminosity. It is warm. It radiates. It slowly cools over billions of years. But it is not fusing. It is not sustained. It is the universe's most elaborate cooling ember. The James Webb Space Telescope, since its launch in 2021, has observed brown dwarfs in extraordinary detail. In 2024, Webb provided the most detailed atmospheric weather maps ever obtained for brown dwarfs, revealing complex banding patterns, silicate clouds, and temperature variations across the surfaces of these objects. The weather patterns look, in some ways, remarkably similar to Jupiter's banded atmosphere, confirming the physical kinship between the two types of objects. The most massive brown dwarfs, those approaching 80 Jupiter masses, sit right at the boundary of hydrogen burning. In some objects at this edge, lithium burning can occur. The detection of lithium in a substellar object is actually used as a diagnostic tool by astronomers to establish that an object is a brown dwarf rather than a true star, because true stars quickly fuse away all of their lithium in their cores, while brown dwarfs, being cooler, preserve it. Jupiter sits well below even the brown dwarf threshold. At 1 Jupiter mass, it is about 13 times too light to fuse even deuterium. But the architecture of its interior is not fundamentally different from a brown dwarf's architecture. Metallic hydrogen, convection, helium differentiation, internal heat generation, a diffuse heavy element core. These are not features that are unique to brown dwarfs. They are features that Jupiter and brown dwarfs share, because Jupiter and brown dwarfs form by the same process, from the same kind of material, through the same gravitational collapse. The difference is quantitative, not qualitative. More mass produces more compression. More compression produces higher temperatures. Higher temperatures, at the threshold, produce fusion. Jupiter has the process running at a level just below where fusion starts. Brown dwarfs have it running at a level just above where deuterium fusion starts. True stars have it running at a level far above where hydrogen fusion sustains indefinitely. It is one continuous physical sequence. Jupiter is not separate from it. Jupiter is on it, at the low end, below the rungs where anything ignites, but on the same ladder. Now let me take you somewhere hypothetical, because the science points there and the implications are worth sitting with. Imagine Jupiter had formed just slightly larger, not 80 times larger, not enormously larger, just large enough to reach the deuterium fusion threshold, around 13 Jupiter masses, or the hydrogen fusion threshold, around 75 to 80 Jupiter masses. What would our solar system look like? It would be a binary star system. Binary star systems are not unusual. In fact, they are arguably more common than single star systems like ours. Estimates vary, but somewhere between 40 and 50% of all Sun-like stars in the Milky Way are in binary or multiple star systems. The famous Alpha Centauri system, our nearest stellar neighbor at 4.37 light-years, is itself a triple star system, containing two Sun-like stars in close orbit around each other, and a smaller red dwarf called Proxima Centauri orbiting at a much greater distance. Our solar system, with its single quiet sun, is the exception rather than the rule. In a binary system with a solar mass primary and a stellar mass secondary at Jupiter's current distance, the two objects would orbit a common center of mass. At Jupiter's current orbital radius of about $5.20 Australian, A stellar companion would complete an orbit of the Sun every 11.86 years, just as Jupiter does now. The gravitational dynamics of the entire solar system would be completely transformed. The inner solar system would be dramatically different in ways that are genuinely hard to calculate. Binary star systems can have stable planetary orbits in two configurations. Either the planet orbits very close to one star, well within the gravitational influence of that star alone, in what is called an S-type orbit, or it orbits very far outside both stars, in a wide circumbinary orbit, what is called a P-type orbit. Planets at intermediate distances, in the middle ground between those two configurations, would be gravitationally destabilized over time. The oscillating gravitational pull of the binary companion would pump energy into the planet's orbit, slowly increasing its eccentricity. Earth's current orbit, at $1 from a sun, might or might not fall into that destabilized zone. It depends on the exact mass of the stellar companion. A very low-mass companion, at the bottom of the brown dwarf range, around 13 Jupiter masses, would have a relatively small gravitational effect on Earth's orbit. A companion closer to the hydrogen-burning threshold, at 75 or 80 Jupiter masses, would have a much larger effect. Some orbital models suggest Earth's orbit could remain relatively stable. Others suggest the eccentricity would be pumped up over tens of millions of years, swinging the planet on an increasingly elliptical path around the Sun, too close in summer and too far in winter, making stable liquid water difficult to maintain across geological timescales. The second effect would be on light and heat. A stellar Jupiter, even a low-mass red dwarf at the bottom of the hydrogen-burning sequence, would add a visible light source to the sky. Not as bright as the Sun, but real. At Jupiter's current distance, it would appear in Earth's sky as an extremely bright object, something like 1,000 times brighter than Venus at its most brilliant. The nights of Earth, which define enormous amounts of biological behavior and have shaped the evolution of every nocturnal species that has ever lived, would be different. There would be no true darkness when the companion was above the horizon. The circadian rhythms of life on Earth are calibrated to a single star system. In a binary, those rhythms would need to accommodate a second irregular light cycle. The third effect would be on the asteroid belt. Jupiter's gravitational resonances currently keep the asteroid belt in a kind of dynamic equilibrium, preventing it from assembling into a planet. A more massive stellar companion at Jupiter's distance would have altered those resonances fundamentally. Some asteroid families that are currently stable might have been injected into Earth-crossing orbits. The rate of large impacts on Earth over geological time might have been significantly higher. The fourth effect, and the most important for the question of life, is stability. Life on Earth has had roughly 3.5 to 4 billion years of relatively stable conditions to develop and diversify. Complex life has existed for somewhere around 500 to 600 million years. That depth of time, that extraordinary span of biological opportunity, required an Earth with relatively stable temperatures, relatively stable orbits, and relatively stable access to liquid water. A binary stellar system, with its more complex gravitational dynamics and its additional heat source, might have provided those conditions, or it might have disrupted them repeatedly, resetting complex life before it could take hold. We do not know which. The honest answer is that the conditions for life in a binary system are not fully understood. Some binary systems, particularly those with wide separations, may be just as hospitable to life as single-star systems. Others, particularly those with close stellar companions, would be genuinely difficult environments for long-lived complex life. Jupiter's hypothetical stellar version at $5.20 sits somewhere in the middle of that spectrum. What we do know is that the difference between the solar system we have and the solar system we might have had is 75 Jupiter masses of hydrogen. That material was present, in principle, in the early solar nebula. It was dispersed by the young sun's radiation before Jupiter could accrete it, and the absence of that material is, in some complicated sense, part of why you are here. There's a thing that Jupiter does, right now, that is worth pausing on. Jupiter is the largest gravitational body in the solar system, other than the Sun, at 318 times the mass of Earth, and at 2.5 times the mass of all the other planets in the solar system combined. Its gravitational field extends throughout the outer solar system and shapes the orbits of thousands of comets and asteroids. Many objects that might otherwise be on collision courses with the inner solar system get intercepted by Jupiter first. In 1994, astronomers watched a comet called Shoemaker-Levy 9 strike Jupiter. The comet had been broken apart by Jupiter's gravity on a previous close pass, fragmenting into 21 pieces that fell into Jupiter's atmosphere over the course of a week in July of that year. The largest impact produced a fireball the size of Earth, visible from Earth-based telescopes. The dark marks left in Jupiter's atmosphere were still visible months later. Had that comet not been captured and destroyed by Jupiter, it might eventually have found its way into the inner solar system. How likely that specific fate would have been is difficult to calculate, but the general principle is clear. Jupiter's mass, sitting at the outer edge of the inner solar system's orbital zone, acts as a gravitational catcher. Comets and asteroids that wander into its region get captured, ejected onto hyperbolic orbits out of the solar system, or fall into Jupiter itself. The flux of large objects reaching the inner planets is reduced by Jupiter's presence. This is not a perfect shield. Some planetary scientists argue that Jupiter also deflects some objects toward the inner solar system that would otherwise have harmlessly passed through the outer regions. The net effect is debated, but the basic dynamic is real. A solar system without a massive outer planet would have significantly different impact dynamics for the inner planets. Now sit with the irony. The object that is intercepting impactors and protecting the inner planets from bombardment is also the object that, had it been 75 times more massive, would have destabilized the inner solar system and possibly prevented life from developing here in the first place. Its failure to become a star is the same property that makes it a guardian of the inner planets. It is precisely massive enough to intercept impactors, and precisely not massive enough to disrupt stable orbits. The two things are not separate. They are one thing. The same mass. The same failure. Two consequences of a single accident of formation. Jupiter did not protect us on purpose. There is no purpose to how a gas giant forms, or to what its mass happens to be. It is physics and timing and the initial conditions of a particular solar nebula 4.6 billion years ago. But the outcome of that physics and timing is a solar system with a stable inner region, a protective outer giant, and a planet in the habitable zone with enough time to evolve complex life. You are one of the things that happened in that time. You are a consequence of Jupiter's failure to be what it almost was. Let me bring this back to your body, the room you are sitting in, the planet you are living on. Everything I have just described is happening right now while you listen to this. Jupiter's interior is contracting by 1 millimeter this year. Helium droplets are falling through layers of metallic hydrogen, somewhere between 20,000 and 50,000 kilometers below the cloud tops. The core, at somewhere between 24,000 and 35,000 degrees Celsius, is radiating heat outward through a diffuse mixing zone of heavy elements. The excess heat is rising through convection currents in the metallic hydrogen, into the molecular hydrogen layer, through the clouds, and outward into the cold space of the outer solar system. The Juno spacecraft is still out there, orbiting Jupiter right now, still collecting data. Its instruments are measuring Jupiter's magnetic field, its gravitational variations, the structure of its atmosphere. The data from Juno is still being processed by scientists at JPL and at institutions around the world. New papers are still being published, new models being refined, new details of Jupiter's interior being worked out. You are alive during the time when human beings are actively, carefully trying to understand what Jupiter is, not just observing it, understanding it, probing its gravity, measuring its magnetic field, sending a spacecraft to orbit it that has survived in one of the most radiation-intense environments in the solar system for nearly a decade. None of this is slowing down on any human perceptible timescale. Jupiter will be doing the same thing in 100 years, in 1,000 years, in 1,000,000 years. The rate of contraction, 1 millimeter per year, is slow enough that you could watch Jupiter for several human lifetimes and see no change at all in its size. The planet appears, on any timescale meaningful to human experience, to be absolutely static. But it is not static. It is alive. in the only way a gas giant can be alive. It is moving inward, slowly, under its own gravity. It is generating heat. It is raining helium. It is convecting. It is radiating. It is actively in the middle of a process that began 4.6 billion years ago and has not yet finished. You are alive during a moment when the solar system's largest planet is still, technically, forming. Not in a way that will produce anything new. Jupiter is not going to grow larger. It is not gaining mass. The raw material is gone. It will never ignite. But the process that produced it, the slow gravitational settling of a massive object under its own weight, is still running. The universe has not finished with Jupiter. Jupiter has not finished cooling. In the long view of planetary science, we are watching Jupiter in the middle of its story, not at the end. I want to be honest here, because the title of this video contains a word that needs careful handling, the word becoming. And it sits next to the word reignite. Let me be precise about what Jupiter is actually doing, and what it is not doing. Jupiter is not becoming more energetic. It is not heating up. It is not approaching ignition. It is cooling. Every year, it radiates more heat than it receives, and every year, its overall thermal energy decreases slightly. The Kelvin-Helmholtz contraction is slowing over time, not accelerating. As the planet cools and the pressure gradient between core and outer layers decreases, the contraction rate decreases with it. Billions of years from now, Jupiter will radiate less excess heat than it does today. Eventually, over timescales comparable to the remaining lifespan of the Sun, Jupiter will reach thermal equilibrium with the surrounding space and the incoming solar radiation. At that point, it will stop contracting, stop radiating excess heat, become, in terms of energy budget, just another cold object reflecting sunlight in the outer solar system. So the honest version of this story is that Jupiter is slowly becoming less like a star, not more. It is on a cooling trajectory, not a heating one. The threshold it almost crossed, the ignition threshold, was available at the moment of formation, when the raw material existed to push it over. That moment is 4.6 billion years in the past. The door closed long ago. It is not opening again. Then what does the title mean? The title means this. The process Jupiter is undergoing right now is the same process that, in objects 75 times more massive, produces stars. The physics inside Jupiter is stellar physics running at planetary scale. When you look at Jupiter's interior, you are looking at the early stages of the same sequence that, if continued with more material, ends in nuclear fusion and stellar luminosity. Jupiter shows you what a star looks like before ignition. It is the dress rehearsal. The mechanism is there. The fuel is there. The architecture is there. The temperature at the core is there, at levels that dwarf the Sun's visible surface. The only thing missing is mass. And mass was the one thing the universe stopped providing. That is what could eventually reignite our entire solar system, means in the context of this title. Not that Jupiter is on track to become a star. It is not. But that everything inside Jupiter is already doing what a prestellar object does. If you could add the missing mass, the same contraction, the same heat, the same interior physics would simply continue upward until it crossed the threshold. No new process would need to begin. The process is already running. It just needs more mass to finish the journey. That distinction between process and threshold is what makes Jupiter strange. The process is there. The threshold is not crossed. And the gap between those two facts is 1 millimeter per year, 4.6 billion years old, and still going. There's one more implication worth naming. In other planetary systems, around other stars, objects similar to Jupiter have formed. In some of those systems, the solar nebula was denser. The dispersal took longer. The proto-Jupiter had more time to accrete. Some of those objects crossed the deuterium threshold and became brown dwarfs. Some crossed the hydrogen threshold and became stars. What we see, across thousands of exoplanet systems now detected, is the full spectrum of outcomes from the same formation process. Planets, brown dwarfs, stars. The path they took was decided by timing and available mass, not by any difference in the physics that set them in motion. Every point on that spectrum is running the same engine, at different scales. Jupiter is the engine running at the quietest scale. Still running, still generating heat, still in some small way, becoming what it never quite became. Let me take one more step back, because the implications of Jupiter's interior reach past our own solar system and into the broader question of how stars and planets form throughout the galaxy. Every star in the Milky Way began as a collapsing cloud of gas, exactly the way Jupiter did. The difference between a star and a Jupiter is only how much gas was available and how long the accretion period lasted. The process is identical at every scale. Gravity pulls gas inward. The gas heats up as it compresses. If enough gas accumulates fast enough, the core temperature crosses the fusion threshold and the object ignites. If not enough gas accumulates, the object settles into the brown dwarf or sub-brown dwarf range and spends the rest of its existence slowly cooling. This means Jupiter is, in a meaningful sense, a frozen snapshot of a stellar formation process. Its interior shows us what the inside of a protostar looks like at the moment, just before ignition would have occurred. If it had occurred, the metallic hydrogen, the convecting fluid, the helium differentiation, the intense core heat. These are not exclusively Jovian features. They are features that a real protostar passes through on its way to ignition. Jupiter got stuck at that phase. The door to ignition never opened, but everything leading up to it is preserved inside the planet, running in slow motion, slowly cooling, slowly settling. The Milky Way contains an estimated 400 billion stars. Each of those stars formed from a collapsing gas cloud. In almost every system, the collapsing cloud did not deposit all of its material into the central star. Some fraction ended up in planets. In the same way our solar nebula produced 8 planets and an enormous number of smaller bodies. Some of those planetary objects in other systems accumulated more gas than Jupiter did. Some crossed the deuterium threshold and became brown dwarfs. Some crossed the hydrogen threshold and became true stellar companions, creating binary or multiple star systems. The Kepler Space Telescope and its successor missions have found thousands of exoplanets. Among them are dozens of objects larger than Jupiter but smaller than the stellar threshold, objects in the range of 5 to 15 Jupiter masses. These are the superjoviants and the brown dwarfs. They represent the continuum between what Jupiter is and what a star is, observed in other systems, confirming that the sequence is real and that objects can form at every point along it. What Jupiter adds to that picture is close-up knowledge. We have spacecraft at Jupiter. We have decades of remote sensing data. We have the Juno gravity measurements of its internal structure. We have the Galileo atmospheric probe entry data. We have radio observations, infrared observations, ultraviolet observations. We know more about the interior physics of Jupiter than we know about the interior of any brown dwarf or any low-mass star, simply because Jupiter is our own backyard. When astronomers build models of how brown dwarfs form and evolve, they calibrate those models against what we know about Jupiter. When they build models of how low-mass stars cool after formation, Jupiter serves as a reference point. The physics of helium rain that applies to Jupiter applies equally to the outer layers of low-mass stars and to the deeper layers of brown dwarfs. Jupiter is not a curiosity at the edge of stellar physics. It is a ground truth anchor for an entire field. In this sense, the solar system's largest planet is doing double duty. From the outside, it is a guardian of the inner planets, the gravitational gatekeeper that catches comets and shapes the asteroid belt. From the inside, it is a physics laboratory, running the processes that build stars, at a scale and proximity that no other object in the universe allows us to study with the detail we can bring to bear on it. We have been sending spacecraft to Jupiter since the 1970s. Pioneer 10 flew past in 1973, Pioneer 11 in 1974, Voyager 1 and 2 in 1979, sending back images of the Great Red Spot and the 4 large Galilean moons that changed how planetary scientists thought about the outer solar system entirely. Galileo orbited from 1995 to 2003 and sent an atmospheric probe deep into Jupiter's cloud layers in 1995, the deepest any probe has ever gone before being crushed. Juno arrived in 2016 and is still operating, still sending back data on the gravitational field, the magnetic field, and the atmospheric structure. Each mission has added a layer of detail to the picture. Each mission has revealed something that previous models did not predict. The diffuse core was Juno's discovery. The shallow lightning from ammonia water clouds was Juno's discovery. The precise structure of the magnetic field, which turns out to be more complex and asymmetric than earlier models suggested, was Juno's discovery. We are still learning what Jupiter is. The planet that has been sitting in the same orbital location for 4.6 billion years, that has been observed by human eyes for tens of thousands of years and by telescopes for 400 years, is still surprising us. The interior we cannot visit directly is being mapped, slowly, through gravity measurements taken by a spacecraft orbiting overhead, one close pass at a time. The picture is getting clearer. It is also getting stranger. That is what happens when you study something closely enough. It always turns out to be more interesting than you first thought. Let me draw together what we have walked through tonight. Jupiter radiates almost twice as much energy as it receives from the Sun specifically. The Cassini measurements put Jupiter's internal heat output at about 7.5 watts per square meter, compared to the roughly 3.4 watts per square meter it receives from the Sun at its orbital distance. That excess heat comes from two main sources. First, the Kelvin-Helmholtz mechanism, the slow gravitational contraction of the planet inward at about 1 millimeter per year, converting gravitational potential energy into heat. This process was proposed in the 19th century to explain the Sun's energy, was found to be wrong for the Sun, but turns out to be real and ongoing inside Jupiter. Second, helium rain, the process by which helium droplets separate from metallic hydrogen in the deep interior and sink toward the core, generating frictional heat as they fall. Together, these two processes have kept Jupiter's internal heat output elevated for 4.6 billion years. Jupiter's interior runs from the visible atmosphere inward through increasingly dense molecular hydrogen, then into a zone of metallic hydrogen beginning at around 20,000 kilometers depth, where the extreme pressure strips electrons from hydrogen atoms and makes the fluid electrically conductive. Below that is the fuzzy, diffuse core revealed by the Juno mission, a zone extending 30 to 50% of the planet's radius, where heavy elements are mixed into the hydrogen, rather than being neatly compacted into a central ball. At the center of that core, temperatures reach somewhere between 24,000 and 35,000 degrees Celsius, between 4 and 6 times hotter than the surface of the Sun. The threshold between a planet and a star is approximately 75 to 80 Jupiter masses for hydrogen fusion. Below about 13 Jupiter masses, an object cannot sustain even deuterium fusion and falls into the sub-brown dwarf category, where Jupiter sits. Above 13 Jupiter masses is the brown dwarf range, where deuterium fusion runs briefly before exhausting its fuel. Above 75 to 80 Jupiter masses is the stellar range, where hydrogen fusion sustains indefinitely. Jupiter, at 1 Jupiter mass, is 75 times below the stellar threshold and about 13 times below even the deuterium threshold. If Jupiter had been 75 times more massive, our solar system would have been a binary star system. The effects on Earth's orbital stability, on the intensity and spectrum of light reaching the inner planets, on the dynamics of the asteroid belt, and on the conditions that allowed life to persist for billions of years, are unknown but significant. Whether life on Earth would have been possible under those conditions is a question planetary scientists and astrobiologists take seriously, without a clean answer. Jupiter's failure to ignite is also the property that makes it a gravitational guardian of the inner solar system. Its mass, sufficient to intercept comets and shape the asteroid belt, is precisely the mass that does not disrupt the stable orbits of the inner planets. Both the protection and the non-disruption are consequences of the same accident of formation. The simple fact that the solar nebula was dispersed before Jupiter could accumulate the additional 74 Jupiter masses it would have needed to cross the ignition threshold. Jupiter is not a planet the way Earth is a planet. It is the bottom of the stellar sequence, formed by the same physical process that creates stars, stopped before the finish line by the simple accident of running out of building material. It is, right now, doing everything a prestellar object does: contracting, generating heat, raining helium, convecting, radiating. The only thing it is not doing is fusing hydrogen, and the only reason it is not fusing hydrogen is that no one added those final 75 Jupiters of mass in time. 1 millimeter per year. That is the pace at which Jupiter is still becoming what it almost was. There is something worth saying before we close. Something about what it means to know that Jupiter is still, right now, releasing its own heat. We tend to think of the solar system as a finished product. The planets are where they are. They are what they are. The sun shines, the planets orbit, comets come and go, and the whole thing runs according to rules that have been stable for billions of years. In the everyday sense, this is true enough. Nothing visible is changing. But underneath that apparent stability, Jupiter is in motion. Its interior is active. Its core is hot. Its helium is slowly separating. It is contracting. It is radiating. It is alive in the only physical sense that matters for a gas giant. It has its own energy source. It is not in equilibrium. It is still in the middle of its own story. This is not going to produce any dramatic event on any human timescale. Jupiter is not going to ignite. It is not going to explode. It is not going to change in any way you or anyone you know will ever see. But the knowledge that it is still in process, still generating, still slowly becoming something slightly different from what it was yesterday, is its own kind of beautiful information. The solar system you live in is not a museum. It is an active system. Even the largest object in it, the one that has been sitting in the same orbital position for 4.6 billion years, is still in the middle of its formation story, still giving off heat it has been generating since before there was a planet called Earth, still raining helium into its own depths, still telling anyone who looks carefully enough that the universe, even in its quietest and most apparently permanent objects, has not finished what it started. Consider this. The Great Red Spot, Jupiter's most famous feature, is a storm that has persisted for at least 190 years by direct observation, and possibly for several hundred years before that. At its largest, it was 3 times the size of Earth. It has been slowly shrinking over the last century, but it has not disappeared. It is still there, driven in part by the internal heat rising from below. What powers the biggest visible storm in the solar system, on a planet with no ocean, no land, no continental edges, no mountains to disrupt airflow, is the heat from a gravitational contraction that began before the Earth's surface solidified. Jupiter is the oldest running engine in the solar system. It started before us. It will run long after us. And the process it is running, Kelvin-Helmholtz contraction, slow and patient and invisible, is the same process that built the sun and every star you have ever looked at in the night sky, just operating at a scale that never crossed the finish line. Tonight, before you fall asleep, I want you to do something. If you are in a place where you can see the sky, or even if you are not, take a moment to remember that Jupiter is up there. On any clear night where it is above the horizon, it is one of the brightest things in the sky. A steady, non-twinkling point of light, brighter than almost any star, hanging in the dark. People have looked at that point of light for tens of thousands of years. Ancient Babylonian astronomers tracked it across the sky and recorded its position with cuneiform marks on clay tablets. The ancient Greeks named it after Zeus. The Romans named it after Jupiter. Every civilization that kept records of the night sky made note of this bright, steady, wandering light. None of them knew what was inside it. None of them knew that beneath that quiet point of light, temperatures were running 4 to 6 times hotter than the surface of the sun. That metallic hydrogen was conducting electricity in vast churning currents deep in the interior, generating a magnetic field 19,000 times stronger than Earth's. That helium was slowly raining downward, one droplet at a time, adding its frictional heat to the interior budget. That the planet was still contracting, still cooling, still in the middle of a formation process that began before Earth's surface solidified. You know these things now. And the strange gift of knowing them is that the ordinary-looking sky becomes a little less ordinary. That point of light is not just a planet. It is the bottom of the stellar sequence, operating at the edge of what a non-star can be. It is a furnace that never lit, a guardian that never ignited, a world that holds more internal heat than it receives from the sun, and has been doing so for longer than Earth has had complex multicellular life. The solar system did not produce a binary star. It produced something stranger, a gas giant that runs stellar physics at planetary scale, a world that came within 75 Jupiters of being a sun, and missed that threshold by a gap that is enormous in absolute terms and vanishingly small in the context of what the universe could have provided. A neighbor that kept the inner solar system stable enough for life to persist, by failing to become the thing it almost was. There's no clean moral to this story, no design purpose, no intent behind the fact that the solar nebula was dispersed before Jupiter could accumulate those final 75 Jupiter masses. The timing was what it was. The physics was what it was. And the result of that timing and that physics, compounded over 4.6 billion years of cooling and contracting and raining helium, is the solar system you live in, the sky you look at, the night you are in right now. You are here, in part, because of an accident of formation that happened in the first few million years of the solar system's history. The atoms in your body were not scattered by the radiation of a second sun. The orbit of your planet was not destabilized by a stellar companion. The calm, stable, predictable sky under which all of Earth's life has evolved, and under which you are listening to this tonight, that sky exists because Jupiter did not light up. Whatever name you give to that, failed star, or sub-brown dwarf, or simply the largest planet in the solar system, it is one of the more remarkable facts in the history of your cosmic address. Sleep well. Jupiter is still out there, doing its slow work, 1 millimeter at a time. Until next time.